Part 3.6 Explicit and implicit finite volume schemes. We can use explicit representation of fluxes in equation 3.16. In this case, we have the following expression, finite volume expression of our main equation. Du by dt in the point I, j, k plus E super n on the surface I plus 1/2 minus E super n on the surface I minus 1/2 over d delta x plus F super n on the surface j plus 1/2 minus F super n on the surface j minus 1/2, and similar expression for j on the surfaces k plus 1/2 minus j on the surface k minus 1/2. From this expression we get this formula. This is the change in the solution at grid point I, j, k during the interval from time n multiplied by delta t to time n plus 1 multiplied by delta t. The formula is the following: delta u sub super n in the point I, j, k is the following. It is the same expression as here, multiplied by minus delta t. For in viscid fluxes, we use the formulas from the previous part. For E, F on J, G on the surfaces I plus 1/2, J plus 1/2, and so on. For viscous parts, we use the formulas similar to the formulas which we used in explicit McCormack's method. This equation is very easy to use, but it is numerical stable only for current Friedrichs Levy numbers, CFL numbers, less than or equal to 1. An estimate of the condition on delta t follows. For one dimension case, delta t should be less than or equal to 1 over this expression, the absolute value of u plus a over delta x plus 2 nu over delta x to the second power. For two-dimension case, the expression is more complicated. Delta t should be less than or equal to 1 over this expression, absolute value of u over delta x plus this, the speed of sound multiplied by the square root from this expression, plus 2 multiplied by nu multiplied by this sum 1 over delta x to the second power plus 1 over delta y to the second power. Here nu is connected with kinetic viscosity, or maybe max of the following expressions: mu, lambda mu over Prandtl number over rho. To remove the CFL restriction on delta t, we need to use an implicit procedure. For simplicity, we consider the two-dimensional case, and let's divide fluxes into two parts: inviscid and viscous part. They are denoted by index C, capital C, and capital V. At first we will focus on the inviscid problem. We can linearize the flux vector using the following formula: E, convective part of E, at the moment of time n plus 1 approximately is equal to E sub c super n plus Jacobian matrix at the moment n d E sub c by du. Delta u super n plus 1. Another form of this expression is ECN plus AN delta u n plus 1. And for the flux in the y direction, we have the following: convective part of F at the moment of time n plus 1 approximately equals to FCN plus this Jacobian Bn delta u n plus 1. Let us express inviscid fluxes in equation 3.1.16. It's the finite volume approximation of the main vector equation. And so we use the following formula: E convective is equal to 1 minus alpha multiplied by E at the moment n plus alpha e n plus 1, which is equal to e convective super n plus alpha a n matrix n delta u super n plus 1, and the convective part flux F is equal to alpha minus identity minus alpha F at the moment n plus alpha convective flux F at the moment n plus 1, and it is equal to F C n plus alpha matrix B n delta u super n plus 1. The parameter alpha determines the order of accuracy of the time derivative. For alpha equaling 1/2, the time derivative is centered, Crank-Nicolson-like, and the second order accurate. Otherwise, it is of first order. At alpha equaling identity, the method is fully implicit, and for alpha greater than 1, it is over-relaxed, but may have better convergence properties depending on the particular simulation. Then we'll split the fluxes according to the sign of the engine values of Jacobins. E on the surface I plus 1/2 is equal, you know this formula, A plus U in the point I plus A minus in the point right side of the cell surface I plus 1. So the first of the equation 3.59 can be written as follows: E C in the point I plus 1/2 is equal to this expression in the moment n plus alpha multiplied by the following expression: A plus on the surface, on the cell surface I plus 1/2 multiplied by delta U n plus 1 in the point I j plus A minus in the point I plus 1/2 multiplied by delta U super n plus 1 at the point I plus 1 on the cell surface, not cell surface, but cell center I plus 1, where for explicit part this we use one of the equations 3.31, 3.34. We have already examined these expressions. Upon substituting this equation in 3.16, I mean these expressions, for d case, we obtain an implicit finite volume representation. Matrix A ij multiplied by delta u n plus 1 I point j plus matrix big B in the point ij delta u n plus 1 I j plus 1 plus C E point E comma j delta u super n plus 1 I j minus 1 plus del d e j delta u n plus 1 I plus 1 j plus e I j multiplied by delta u n plus 1 I minus 1 j is equal to the delta u n I comma j, where delta u n I j is solution change calculated explicitly by equation 3.54. This expression, which is calculated explicitly. And other matrices are calculated by the following formulas. Big A ij is equal to identity matrix I plus alpha delta t by dx multiplied by this difference. A plus is the point I plus 1/2 minus A minus in the point on the cell point I minus 1/2 plus I delta t over delta y, B plus in the on the cell j plus 1/2 minus B minus n I j minus 1/2. Matrix B is equal to alpha delta t over delta y, B minus on the cell j plus 1/2, big C I comma j is equal to minus alpha delta t by over d delta y, b plus on the cell j minus 1/2, and the similar equations for d and e, big D and big DE, which are calculated by a minus, a plus, respectively in the point cell I plus 1/2 and cell I minus 1/2.